Welcome to the next video in a course in real analysis. This is lesson 7, where just somewhat thematically we're going to study theorems that have to do with the real numbers and how the natural numbers kind of interact with them. And at the end we're going to have exercises. So this material is where my lectures will finally start aligning with the content of the textbook. And so I can start to recommend some reading as we go along. So I recommend before watching this video, although the order isn't terribly important, but it might help to at least try to read section 4.1 of the textbook. You will almost certainly notice that many of the things in section 4.1 are things that I've already covered in previous videos, but seeing another presentation of the same stuff can be helpful. You'll probably also find some things that I did not cover. So yeah, go ahead, do that, and then finish this video. Now, as we've talked about, I'm not going to discuss things that are specifically about the natural numbers because we're going to just take those for granted. But there are ways in which the natural numbers and the real numbers kind of interact. So if you think about the real axis, and maybe we place 0 here, intuitively, right, our instincts tell us that you could pick an arbitrarily large real number y, and even if you then picked an extremely tiny positive real number epsilon, then if you just took a large enough number of steps, right? So this would be a natural number, right? Because whenever you're counting stuff, that tends to be a natural number. So if you imagine that every one of these little tick marks is another step of size epsilon, then the number of steps that we took here, which we could call n, intuitively, right, just thinking with our geometric instincts, no matter how big y is and no matter how small epsilon is, as long as it's positive, then you could choose a large enough, specifically natural number that would, if you took all those steps of size epsilon, you would get a quantity that finally is bigger than y. So what we're saying is that for every real number y and any positive real number epsilon, there exists a natural number n such that n epsilon is bigger than y. That's the instinct here. And this is, in particular, like, if we were talking about, a real number such that epsilon times this real number is bigger than y, that'd be a much easier task, right? But no, we specifically want a natural number. And this is going to come up, right? Eventually we're going to start talking about sequences of real numbers, and sequences kind of intrinsically have to do with the natural numbers, and so on. So there's a good reason why we're particularly interested in an idea like this, and specifically having to do with the natural numbers. So we really insist on this thing that we get is a natural number. So we really need this result for later purposes. So now that we've stated that in roughly intuitive way and a slightly more formal way, here is the theorem stating basically those same ideas, and we're now going to give it a rigorous proof. So again, leveraging a bit of geometric intuition to help guide us in how we do this proof, right? Epsilon's there, maybe y is there, and what we can think is that, well, we've actually got a bunch of things here, right? 2 epsilon is there, 3 epsilon is there, and so on. And then there may be some point at which we have an n epsilon to the right and a n plus 1 epsilon after that. And in a sense, what the geometry maybe suggests is that y is like a separator between the set of all n epsilon on the left and some other n epsilons on the right. But in fact, actually, like in a way, all we want to do is demonstrate that this set over here is non-empty. Well, we have the least upper bound property, and so maybe what we want to do is to focus on the set over here to the left. And so effectively what we want to prove about this is that the set that is to the left here is not the whole set, that there are some other values of n epsilon, so to speak. So maybe for contradiction, we could go ahead and assume that this set, right, the set of all n epsilon, let's assume that it is bounded above by y, that the, right, sort of corresponding to the picture, that would mean that the entire set is located to the left of the value y on the number line. So we'll assume that for contradiction. When we get a contradiction, it'll mean that it is not bounded above by y, and therefore there must exist some value in the set which is bigger than y, and that is essentially what we want to show. Okay, well, we know that the set S, which is the set of all n epsilon, when epsilon exists, of course, we assume that it is some positive real number. It doesn't matter which one, so that exists. And we can just set n equal to 1, and then n epsilon, right? Like 1 epsilon is a number in the set X, so it's non-empty, right? That's very easy to see. It's also bounded above due to the assumption that we just made that y is essentially an upper bound on the set. So because it is bounded above and non-empty, it must have a supremum. We'll call that alpha. Now from here, where do we go? It may not be obvious, but perhaps we could sort of use the intuition that we want to talk about values that are close to the supremum, because we know, again, sort of talking about this geometric picture that we're trying to kind of leverage for our proof, that, okay, so y is an upper bound, alpha is the least upper bound on our set. Oh, I don't know why I said sup y. I guess I just got my letters confused, but that should be sup s. Anyway, so alpha is the least upper bound, so it is some value less than or equal to y. In any case, we're probably really interested in values that are close to this alpha, because if we can find some, I don't know what we want to call it, m epsilon, just so that we, don't call everything n. But anyway, so if we get a value that's really close to that alpha, and we take one step beyond it, right? If we just go to like m plus 1 epsilon, or, maybe it lands out here. But in any case, right, if we can kind of get values that are real close to alpha, and then take integer steps past that, then it seems like we'll be able to perhaps derive a contradiction, right? If, find a value that is beyond y, right? So that's kind of the intuition. So if that's what we're trying to do, then we can maybe go down from alpha by a distance of exactly epsilon, right? Epsilon seems related. We want to go down from alpha. Let's maybe go down by that much. Now, we know by what we have talked about in previous videos dealing with suprema, that when you take the supremum and you go down by any amount, then that is no longer an upper bound, and so there must be an element of the set which is bigger than it. So maybe that's a decent picture of what we're kind of talking about here. And then, we can see this in one of two ways, right? Like we could think about taking an extra step, or the same idea is kind of reflected in the algebra step, where we add epsilon to the other side of this inequality, and we get that n epsilon plus epsilon is bigger than alpha, and then we can factor that, so n plus 1 epsilon is bigger than alpha. But notice, and this is where somewhat the properties of natural numbers are important here, but that n plus 1 is a natural number, right? It's somewhat important to note that, after all, it is only because n plus 1 is a natural number that n plus 1 epsilon, we can say, is in the set S, right? Remember, S was natural numbers times epsilon. So because n is a natural number, therefore n plus 1 is a natural number, therefore this element is in the set S by definition. Now, Because we have constructed this value, which is bigger than alpha and in the set S, therefore alpha is not an upper bound on the set S, but it was defined in the first place as the supremum, meaning that it is an upper bound. Okay, we have a contradiction and the proof is complete. Okay, now that we know that in a sense natural numbers can be very large, right, bigger than any real number that you pick. Okay, the previous theorem said a little bit more than that, but that's just a rough kind of summary of the content there. Well, let's also try to go the other way. It'll also be useful when we start talking about sequences to know that, for instance, 1 over n can be made very small. So in particular, what we're going to say is that if you pick any positive real number epsilon, so you want to kind of imagine that if 0 is here and epsilon is tiny, very, very small, but positive, then we can always find a value n, right? We can find a natural number n such that 1 over n is even smaller. That's what we'd like to show in this theorem. Okay, that is equivalent, right? If we have a given epsilon, and we are trying to find a value of n such that this inequality is satisfied, it is equivalent to finding an n such that this inequality is satisfied. And now this looks a whole lot like the previous theorem, because after all, it has an epsilon in it. We're trying to find a large value of n epsilon, in particular bigger than 1 in this particular application. And so we know that a choice of such an n must exist by the previous theorem. And so, here what I'm indicating is that if we take that previous theorem and everywhere that we see y, we simply substitute the value 1, then the theorem applies exactly to this situation. And we can, then we know that a value of n exists like this, and then, and that is essentially the end of the proof, because we know that since an n exists like this, then if we simply take that n, divide back to the other side, then we have exactly what we set out to show. And I'll just point out some vocabulary. The textbook uses the phrase Archimedean property to refer to a particular result that is similar to some of the results that we have here. At least some authors call the Archimedean property the theorem that I have called any distance by enough steps. So there's just kind of like not perfect uniformity about what these names mean. So anyway, if you take what I called any distance by enough steps and you specifically apply that to when the value x there is 1, or rather, I guess I think I called it y, so I should probably say when y is set to 1, then you get what the book calls the Archimedean property. But so just be aware that when you see the Archimedean property in other settings, it might be this, it might be what the book is talking about, or it might be some slight variation on that. So, having now introduced the topic, then we can do some exercises. So here's the first exercise. Prove that between any two real numbers is specifically a rational number, right? It's easy to show that between any two real numbers is a real number. You could just find the average, but we want specifically a rational number, and that's gonna be harder to do. And I don't think you can necessarily use any of the, or, it's not an immediate consequence of the things that we've shown earlier in this video, but there is a style of proof that you could try to replicate for this. So Thinking a bit geometrically, let's draw a number line with a 0 here. Let's at least initially, right? We don't want this in general, but at least to get started and to have, reasonably simple steps. Let's put everything to the right of 0. And then, so we've got A is bigger than 0 and B is bigger than A. And these are our two real numbers. And let's talk about the distance between them, which is B minus A. And perhaps what you'd like to do to find a rational number in between A and B is to imagine, well, maybe, if I kind of take epsilon to be this distance, I can find a rational number, and let's call that 1 over m. So we can find this rational number, which is strictly smaller than epsilon. And then what we could do is use the other theorem that we've proved in this video to say that there's some number of steps. Maybe we'll say that there are n steps of size 1 over m, such that we get above a, right? So we know that there is some choice of n such that n over m effectively is bigger than a. Now, I think that if you did all of this, you might run into a slight difficulty, like a slight edge case. So although I think all of this makes sense, the picture is nice, you might make things a little bit more manageable, or things might come out just a little bit nicer if rather than using steps, rather than using epsilon as b minus a, the distance between them, it might actually be better if you made it even smaller, right? If you took even smaller step sizes just to get a strictly smaller step size. Basically the issue is just that if you took the distance to be b minus a, then possibly when you do all your steps, you could land right at a. And if what we really want is a number that is strictly in between A and B, then you wouldn't want to be on A. If you took another step, then you'd actually land on B, because your step size is the size of the distance between A and B, and you'd never get the value that is actually strictly inside the interval between A and B. So that's why maybe you want to take steps that are just a bit smaller than that, so that you are guaranteed to land strictly inside the interval. So anyway, there you go. There's some hints. And then at that point, one thing that is kind of a reason why it's convenient to do all of this to the right of 0 is just so that we know that n is a positive natural number, and then we can say that because it is a subset of the natural numbers, then we know that it has a least element, right? If we were going to the left and to the right, then you'd need integers, possibly negative integers. And although I'm sure that, yes, that proof can be amended, it just gets a little complicated. So it's nicer just to know that we have positive integers, right? And this is a set of positive integers that you get from, all of these steps. And then it must have a least element, right? Which we're effectively saying, right? When we talk about that you've got this 1 over m, we're taking a bunch of steps. Eventually you get to A and B, and eventually, we're saying that there is some number, right? Out here, there is some number, n, such that n over m is bigger than a. So that's kind of what we're getting. But we don't know where it's located, right? When we just say that there exists a number like that, for all we know, it's way over here or over here. Who knows, right? And so the point is, you're going to want to find a least, right? Because we want to fall inside of this interval. So at this point, when you know that there is an n like this, and you know that it is a natural number, you can form the set of all such n and take its least element, and then reason that way, right? So once you know that you have the least n satisfying this equation, and you know that there is some n, so, right? Anyway, You'll have that A is strictly bigger than, other way around, that A is strictly smaller than this choice of n that you've just made. But then what you still need to show is that this number is smaller than B. And for that part, it'll, I think like the geometry kind of shows you that for that part, you really need to know that n was chosen as the least integer satisfying all of these conditions. So once you know that n is the least, and you're trying to show that n over m is smaller than b, then maybe try to proceed by contradiction. And think back about what you know about 1 over m, right? Because it was important that that is smaller than the distance between A and B. So that's an important thing to know around what we're doing here. And if you imagine, for contradiction, that this n over m were somehow bigger than B, bigger than or equal to B, that's going to run into a contradiction because of the, something that we know about m being smaller than the distance between A and B. In particular, see if you can maybe obtain this inequality. If you could obtain this inequality, then you know that you actually have a value, a natural number value in the numerator, which is which gets you a rational number that is bigger than A, but it is smaller, right? Because you'll know that n minus 1 over m is smaller than n over m. And so then this will contradict the idea that n was chosen as the least natural number satisfying this condition. So there, right, this is all just to give you some ideas about how to go through this proof. It's not meant to be a full demonstration or anything like that, but just to give you some ideas about what to try here. Okay, and that should hopefully get you to the contradiction that sort of concludes this portion of the proof. Then you still need to come back and consider what happens when A is not greater than 0, so less than or equal to 0. But once you have, right, like basically use what you've shown, right? Use the result for positive values of A to help you handle the case for non-positive values of A. In particular, if A is non-positive, then try, shifting A over to the positive side. You'll have to think about how to do that and how, so on. But shift it over to the positive side, obtain the result that we're trying to show over there, and then shift everything back to where it came from at the end. Okay, so let's now talk about the second exercise, which is to prove that every real number is between some two consecutive integers. That is to say, if you pick an arbitrary real number r, then there must exist some integer n such that r is between n minus 1 and n, possibly inclusive on the left. It's not important that it's possibly inclusive on the left. We could have restated this so that it is inclusive on the right. But the point is just that, when you pick an arbitrary real number, there is a possibility that it just is an integer. So when we say that a real number is always between some two integers, on one end it could be inclusive. But anyway, how are you going to show this? Well, let's take the assumption that our real number is strictly bigger than 0. We know from earlier stuff that there must exist some natural number, which is bigger than r. You can form the set of all such natural numbers, know that it has a minimum, just like before. And then for this minimum, right, for the choice that we just made, you can show that it is the thing that satisfies this inequality. And then finally, once you have all that, then you can generalize to the case where R is non-positive. And finally, I'd like to end on an invitation to ask questions. So if you found anything confusing in this video or in similar portions of the textbook, then feel free to leave a question. If I can address it in the comments, then I will. But if it needs more, then I may make a video and include it in the playlist.